It is a truth universally acknowledged that a computer in possession of a hot chip must be in want of a good cooling system. The problem of cooling has been an issue for as long as computers existed, and tightly intertwines with semiconductor history. To riff off a very famous computer designer who shall appear later, it begins with scientists and ends with plumbers. In today's video, a whirlwind tour of the many methods we have employed over the years to keep our computers cool. But first, I want to remind you about the Asianometry Patreon and the Early Access tier. Members get to see new videos first and get the references attached. Early Access directly supports the channel and really helps. Thank you, and on with the show. The first digital computers used vacuum tubes. These vacuum tubes switched signals far faster than their predecessors, electromagnetic relays that had to physically open and close. The downside, however, was that they ran hot. Take the ENIAC. The 30-ton computer consumed about 150 kilowatts of power and put out approximately 150 to 174 kilowatts of heat, or roughly equivalent to 110 portable space heaters. High temperatures can blow out a vacuum tube via thermal stress or filament burnout, so they installed air conditioning inside the computer room. Powerful blowers were also added to blow cool air over the tubes. Even so, temperatures in the room regularly reached 49 degrees Celsius. A few years later, the computer was moved from Philadelphia, where it was built, to an Army location in Maryland. The new room had issues with air circulation, which caused the tubes to regularly burn out, inflicting untold grief upon its operators. One major reason why the tubes burnt out so often had to do with their arrangement. The ENIAC designers packed the machine's 17,000 or so vacuum tubes together very tightly, which caused heat to build up. This emphasis on packaging density would be a common issue over the years. IBM's best-selling 604 calculating punch machine, sold in 1948, had 1,400 vacuum tubes. And to simplify the mass production process, IBM engineers created these packages called pluggable units. Each unit had a mini vacuum tube bundled together with accompanying resistors and capacitors. The units made it far easier to replace a burnt vacuum tube, but also greatly increased the unit's density and thus its heat output. The computer, more like a calculating punch machine, but whatever, put out 6.2 kilowatts of heat, which necessitated air conditioning and blowers on both sides of the machine. And since the rooms sucked in room air and room air is dirty, filters were built into the sides as well. In 1948, Bell Labs announced the creation of the transistor. The New York Times ran an article about the event, and it was the first time the word transistor ever appeared in print. The now famous article notes that this new device would give off no heat, saying no heat is developed as in a vacuum tube. Another contemporary news article also notes that the transistor was non-heating. So the general feeling at the time was that this new solid-state device would free us from all the heat worries associated with vacuum tubes. Sadly, that dream of a heat-free computer turned out to be a naive one. Computer makers started packing these non-heating transistors more tightly together, a job made somewhat easier thanks to the invention of the integrated circuit at the end of the 1950s. This became a consistent theme in computer history. People are always trying to package more devices together, from less than 100 to 1,000, 10,000, 100,000, and beyond. And with more integration, we always get more heat. How do we deal with that? Liquid cooling has long been used for the purpose of cooling vacuum tubes. It predates the ENIAC itself. In 1935, a researcher named I.E. Moromtsev published work on cooling high-powered vacuum tubes with water, though he noted that the techniques he used had been around since at least the prior decade. Then, in the 1950s, the US military started investing in more powerful communications and control systems for missiles and aircraft. Such systems needed high-powered vacuum tubes for creating or amplifying powerful analog signals. An example of such a tube was the magnetron tube, which was used for generating microwave signals. These high-powered devices not only ran hot, they operated in high temperature conditions, making cooling a necessity. And air is not a very good medium for removing that heat. A volume of liquid can absorb 1,000 to 3,500 times more heat energy than the same volume of air before its temperature rises a single degree. Liquids are also better suited for transferring away heat. Their thermal conductivity, meaning their ability to conduct or transfer heat, is 15 to 25 times higher than that of air. So what liquid to use? The ideal heat transfer fluid would be water, but unfortunately, water corrodes and cannot be brought into direct contact with the circuitry. This spurred new research into cooling liquids like 3M's Fluorinert, DuPont's Freons, or Dow Corning's DCs. Various evaporative cooling mechanisms were developed during this time. One setup sprayed liquid onto the tubes. Other setups submerged the electronics in pools, boiling off the liquid. These type setups, where the coolant transitions between liquid and gas, are today called two-phase immersion. The liquid vaporizes, hits a condenser to release its heat, and then turns back into a liquid. By contrast, a cooling system where a liquid coolant remains liquid the whole time, its heat offloaded to a second water loop or something, is a one-phase immersion system. Modern two-phase systems try to recover and reuse the evaporated coolant. Back then, however, they discarded it. Which makes me cringe, considering how environmentally unfriendly those liquids turned out to be. But hey, the 1950s were crazy, dude. Another cooling system that emerged during this time was the cold plate. It stems from an early cooling challenge. People can blow cool air through a computer, but whether that air was actually hitting the computer's hotspots was anyone's guess. This uncertainty caused many sad times. So they built well-defined metal channels and ducts to funnel cool air to hotspots. This allowed the designers to predictably design airflow. And it worked very well at cooling tightly packed conditions inside missiles and other gear. By the end of the decade, however, transistors started to replace many of these vacuum tubes. Their smaller size and tighter packaging made it far trickier to identify and cool these hotspots. In the days before computational fluid dynamics, engineers had to work out a transistor's heat profiles by hand. First, they take the physical design of the transistor and its packaging. Then they model the spread of heat from the transistor's inner junction outwards. They look at what quote-unquote road that heat is essentially traveling on and allocate a thermal resistance score to those roads based on its materials. A circuit analysis technique can then be used to find the total thermal resistance from junction to the air. This gives them a prediction of the transistor's final temperature necessary to evaluate its overall safety. In 1964, IBM introduced the System 360 line of mainframes, the most powerful of which was the Model 91, which came a bit later. That computer is noted for introducing liquid cooling for the first time, albeit in a hybrid format. Most computers in the era blew air over consecutive rows of chips on the circuit boards, but such an arrangement also meant that the air would get hotter and hotter as it progressed through the boards. So, the Model 91 places air-water heat exchangers between the boards, which brought down the air temperature rise from 29 degrees to 7 degrees Celsius. Today, these arrangements are called hybrid or indirect liquid cooling systems. IBM people later recognized that the quality of the water mattered in cooling efficiency, and since customer water can be somewhat dodgy, they built a two-loop system. The inner loop is a closed one with purified water going to and from the circuits carrying heat, and then exchanges heat with the outer loop, which was filled with customer water. These coolant distribution units, as they were called, first emerged in 1968, built for a customer facility at Columbia University, and its basic structure has remained in use for decades soon after. Computer designers continued to push the envelope in terms of how close they can bring the liquid to the circuitry without actually getting them wet. In 1977, Honeywell presented their top-end Model 6685 computer, armed with a feature they called true liquid cooling. In this setup, the liquid water is brought directly to the chips to exchange heat with them. This is in contrast with what IBM had done with the Model 91, where water cools down the air in between the chips. If you ask me, calling it true liquid cooling is somewhat misleading, since the water isn't touching the chips. Today we call it direct liquid cooling. Honeywell pulled this off with a frame called a Silent Liquid Integral Cooler, or SLIC. Maybe I'll call it SLIC. The SLIC is a metal plate that brought water to the microelectronics package via a connected hose. An auto shutoff feature made it easy to replace packages without causing a watery mess. The result was a fascinatingly quiet system. Honeywell discussed later how the liquid cooling system let their designers stuff even more logic chips even more tightly together. Guess you can never have enough. Around this time, IBM began working on new ways to package multiple chips together. Their work yielded these multi-chip modules, where several smaller chips are bundled together in one big packages, basically what the industry today calls chiplets. Heat was a major concern. Having so many chips on a single substrate dramatically raised the package's overall power density, necessitating new heat dissipation methods. In the late 1970s, IBM produced the thermal conduction module, or TCM, for this problem. The TCM tried to maximize contact between a water-filled cold plate and the chip package. The first TCM did this using a small, helium-filled chamber with a tiny spring-loaded piston inside. Yes, I know, a piston might sound excessive, but that was how IBM engineers solved the issue of accommodating different package heights while also maximizing physical contact with the chips. Heat conducted through the piston to the cold plate. The TCM made it possible to cool down packages as heat dense as 64 watts per square centimeter. They eventually made 3 generations of it, replacing the somewhat excessive piston with a thermal paste. The major trend of the 1980s was very large-scale integration, which put tens or hundreds of thousands of components onto a single die. This was possible thanks to the popularity of the PC and Moore's law pushing the envelope, as well as breakthrough technology improvements in lithography, crystal growth, and computer-aided IC design. But stuffing so many devices so tightly onto a die also rapidly increased heat densities. Chip surface temperatures started to reach 50 or even 100 degrees Celsius. Computer designers were unsure if they can dissipate all this heat, calling it the thermal barrier. Even more worryingly, they looked at charts that extrapolated forth to a not-so-distant future when chips' heat fluxes matched that of the surface of the sun. This heat apocalypse was temporarily canceled thanks to a major switch by the semiconductor industry. Up until the 1980s, most American semiconductor makers used one of 2 types of transistors for large-scale integrated products: bipolar transistors, or N-channel metal oxide semiconductor field effect transistors, or NMOS. But a new technology was gaining traction in the market: complementary metal oxide semiconductors, or CMOS. It pairs the aforementioned NMOS with a P-channel MOSFET, or PMOS. CMOS has been around, having been first proposed by Frank Wanless and Tom Sa of Fairchild Semiconductor back in 1962. And from the start, it was noted for its low power draw and high noise immunity. But those advantages were counterbalanced by its slower switching speeds and roughly 20% higher production costs compared to NMOS due to larger dies and lower yields. So for the first 20 years after its invention, CMOS remained a specialty semiconductor technology for niche, low-power devices like watches, calculators, or military radios. This situation began to change in 1980. NMOS's power and heat limitations had started to make it more expensive to produce, and semiconductor makers developed new methodologies to improve CMOS's speed and manufacturability. But what designers most appreciated was CMOS's substantially lower power draw, which let it run up to 20 degrees Celsius cooler than NMOS. And for designers, it means that we can pack together even more transistors. The Japanese memory makers were amongst the first to realize these advantages, with Hitachi waving its magic wand to unveil a CMOS DRAM in 1980. Intel unveiled a CMOS DRAM of their own in 1982. Then in 1985, Intel used CMOS for their Intel 386 CPU, and that turned out to be a breakthrough chip. 2 years later, in 1987, annual sales of CMOS chips overtakes that of NMOS. The switch over from NMOS to CMOS was a momentous step in computer history. CMOS's lower power draw and Dennard scaling, which we will talk about later, helped keep microcomputers and even workstations on the Moore's Law trajectory while retaining a light touch with cooling. But throughout the 1980s, there was one conspicuous holdout: the supercomputers. No video on computer cooling is sufficient without mentioning the supercomputers, and especially the Cray. Even before the Cray 1 was finished, its legendary designer Seymour Cray was moving on to something even faster. The Cray 2 would have a clock cycle time of just 4.1 nanoseconds, a third that of its predecessor, giving it a peak performance of 1.9 gigaflops. Like with the Cray 1, the Cray 2 used emitter-coupled logic, a bipolar transistor-based digital logic integrated circuit known for its unmatched speed. ECLs, as they're called, achieve that high speed by leveraging a special feature of the bipolar transistor that lets them constantly operate in a special responsive state. Thus, you achieve ultra-fast switching times, but at the cost of high power consumption and heat generation, since they are basically on like all the time, like how you always keep your foot on the pedal whilst on the freeway. But ECLs alone wasn't going to get you there. The Cray 2's desired clock cycle time necessitated the wires connecting its ECL chips to get even shorter, from 48 inches to 16 inches, which means packing the chips together even tighter. Both the Cray 1 and Cray 2 put its ECL chips on circuit boards and packed the boards into modules, essentially like the pluggable units I mentioned earlier on the IBM 604. The modules on the Cray 1 had 1 to 2 circuit boards bound together, but the Cray 2 went further, stacking a baffling 8 circuit boards together in a concoction that makes me imagine a Cubano pressed sandwich. How do we cool such a spicy silicon sandwich? The Cray 1's modules had cold bars in between its boards, cold plates with freon or liquid nitrogen flowing inside. But the Cray 2's boards were too tightly packed together for that. So Seymour Cray proposed to stack the modules inside a literal aquarium and pour coolant liquid over them, with the liquid making direct contact with the circuits. In other words, immersion. His team thought that this was, well, Cray. But Seymour had been familiar with liquid immersion from his former employer Control Data and proposed to use a clear, non-conductive, fluorocarbon-based liquid called Fluorinert. Fluorinert was developed by 3M back in the 1940s. Movie aficionados might recall it from the James Cameron flick The Abyss, which showed a rat breathing in a bath of oxygenated Fluorinert. In the final Cray 2 design, the iconic semicircle chassis housed 14 vertical towers, with each vertical tower made up of 24 modules, so 336 modules stored inside the semicircle in total. During operation, Fluorinert liquid is pumped into and up the vertical module towers at a rate of about 70 gallons per minute, and then flows between the module stacks like a waterfall, making direct contact with the chips. After this, the liquid, now about 5 to 6 degrees Celsius warmer, goes to a heat exchanger where its heat can be offloaded to a normal water loop. It took 4 years for Cray Research to work out all the kinks in the Cray 2 design. Upon its release in 1985, the always quotable Seymour Cray reflected upon his career. "I began as a computer scientist, became an engineer, and am now a plumber." The Cray 2's year-long delays and ridiculous engineering contributed to its final $12 to $17 million price tag. Amazingly, Cray still sold 27 of these puppies, though it was later eclipsed by the parallelized Cray XMP. A few companies explored immersion for their supercomputers. A famous one was Control Data, which did an immersion cooling system for their own supercomputer, the ETA-10. But the short-lived ETA-10 used liquid nitrogen as its coolant. And when Cray Research's star designer Steve Chen left to start his own thing with IBM called Supercomputer Systems, their first new supercomputer, the SSI-1, featured a unique showerhead-like jet that sprayed pressurized coolant, I think it was water, onto the chips. But few followed in Cray's direct footsteps and used dielectric liquids. Such liquids were extremely expensive, had possible cancer risks, and cannot conduct heat as well as water can. And in the end, CMOS transistors just got small and good enough. ECL switched ultra-fast, but it ultimately made more sense to network together many ordinary CMOS chips to do big tasks in parallel. Even IBM made the switch in 1993, completing the conquest of CMOS. CMOS chips can be cooled with simple cold plates, heat sinks, or air blowers. This was another major benefit because it let computer makers and compute centers tear out their expensive water cooling systems. Today, many data centers are cooled via air, with large air conditioning units pushing air over the server racks. I don't think that would be possible if those chips ran bipolar ECL. So CMOS put cooling technology on ice, though IBM in the 1990s did do some interesting things with servers that refrigerated CMOS processors, based on work dating back to the 1960s and 70s when they were really into computers based on Josephson superconducting circuits. If only such a time can extend forever, but it couldn't, thanks to Dennard. I did a whole video about the end of Dennard scaling, but let me summarize. When transistors get smaller, they require less voltage to switch and can also switch faster because the channels between the source and drain get smaller. So the result is that we can put more transistors on a unit area on the chip while still using the same amount of power. People thought that this trend would last forever, but like all good things, they do not. The layer of oxide material between the transistor's gate and its channel had shrunk to mere nanometers thick. This presented big challenges in fabrication. The transistor also just got so small that the gate no longer works the way it should. A current is left running through even while the gate is quote-unquote closed, causing power consumption and heat generation to skyrocket. People first noticed this in the late 1990s at the 90 nanometer node, but it was not until 2004 and 2005 when the industry giants like Intel and AMD publicly recognized it, shifting to a new multi-core paradigm. Work can still be done to retain control over the circuit. I discussed a few of these in prior videos like the high-K metal gate, the FinFET, and the gate-all-around transistor. But these expensive innovations do not replace Dennard scaling. So now the chips are once again eating power and getting hotter, and the trend has caused a few people to bring the art of computer cooling back out of the refrigerator. In 2008, IBM publicized the Power 575 supercomputer node. It was a server that can be stored inside a rack frame and boasted a cooling system that used water-filled cold plates that absorbed 80% of the chip's heat. They call it a back-to-the-future moment, claiming that it can reduce power consumption in data centers by 40% and raise energy efficiency by 3 times. A year later, they talked about the Aquasar supercomputer prototype. Made in collaboration with ETH Zurich in Switzerland, the computer features a unique hot water cooling system. The waste heat exchanged from the computer can be recycled to heat buildings in an attempt to recover some of the energy cost. The Japanese also did interesting things in liquid cooling. One fun research prototype involved coating a circuit board with a micrometer thin layer of perylene insulation to enable full immersion in water. They even ran an experiment that left a coated circuit board underwater in the Tokyo Bay for over 50 days. Fun, but probably not the future. Can't imagine too many supercomputers left unattended at the bottom of the sea. More relevant to what is going on today, the Tokyo Tech University runs a series of supercomputers called the Tsupame. In the early 2010s, they presented the fluid cooling version of the Tsubame, or as I shall always call it, the KFC. KFC adds oil-based immersion cooling, so completely immersing its compute nodes, which include 2 Intel CPUs, 4 NVIDIA Tesla K20 GPUs, SSDs, and memory, in a pool of low-viscosity synthetic oil. The paper notes how the racks need to be prepared with the removal of physical moving parts like the cooling fans, as well as a gentle dip in tempura batter. The final system had a measured power usage efficiency of 1.29 and could do 4.5 gigaflops per watt, which was quite good. So liquid cooling, even liquid immersion cooling, has been around, but its complexity has somewhat discouraged people from adopting it. The Gen AI era has changed that, in my opinion. In 2020, a 10th generation desktop Intel CPU's maximum heat generation in real-world conditions under high load was about 125 watts. Hot, but somewhat reasonable, especially with the rise of multi-core programs. But NVIDIA's AI accelerators, with their need to do trillions of calculations per second, are blowing these heat numbers out of the water. The NVIDIA H100 puts out 700 watts of heat. Its successor, the B200 accelerator, does 1000 watts. It's not just a lot of energy, but also a lot of heat, and I don't think heat sinks are good enough. I recently visited Firmus Technologies, an AI factory systems company in Singapore, and got to take a look at the single-phase oil-based immersion cooling system that they've developed for these heat issues. If you're ever allowed into an air-cooled data hall, the first thing you notice is just how loud it is. It's like as if you're watching a Christopher Nolan movie in IMAX and he set the score to 1,000 vacuum cleaners. The fans are not only deafening but also bring in dust and other particles. They feature moving mechanical parts prone to breaking down while also consuming a larger percentage of energy than most people would like, 30 to 40%. So Firmus takes off the fans and other moving parts that are shipped with the GPU modules. They then immerse the hardware into a liquid coolant, a lubricant or synthetic oil somewhat like that used for the Tsubame KFC supercomputer I mentioned earlier. The result is a data hall that is eerily silent. Along with the space-age visual design and lighting, the whole experience is a bit surreal, like something out of a 1970s science fiction movie. Then you lift one of the lids and see these NVIDIA GPUs worth thousands or tens of thousands of dollars just sitting at the bottom of a tank of liquid. Is that okay? Can they do that? I guess they can. Per Firmus, their immersion cooling setup delivers up to 60% reduction in energy costs compared to traditional settings. But consider what is coming up next. The guys at SemiAnalysis have estimated that the heat profiles of NVIDIA's next-gen 3nm Rubin chips, scheduled for 2026, will reach a staggering 1,800 watts. Chips from AMD and the hyperscalers will have similar metrics. Heat profiles of that magnitude will likely require a suite of complementary schemes, so maybe a single-phase liquid immersion combined with cold plates mounted right on GPU chips, something known as direct-to-chip, or maybe something else along with that, microfluidics maybe. One thing is for certain, whatever clever cooling contraptions that the AI factories come up with, chip makers will just use to push silicon even hotter. The hot and cold cycle rolls on. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.